The overwhelming rise in foreclosure rates is one of the top news headlines today. According to RealtyTrack, foreclosures are up 75% from 2006, and the estimated effect is a $1.2 trillion loss in property values in 2008. The Department of Housing and Urban Development is already hard at work trying to help American families save their homes. There are currently thousands of HUD-approved housing counseling agencies throughout the United States. And just 2 weeks ago, the Federal Housing Administration mailed letters to 280,000 at-risk families currently facing the first reset of their adjustable rate mortgages, with 570,000 more letters to be mailed by the end of September. This map shows us the results of a hotspot analysis created using the Spatial Statistics Toolbox. I've used the hotspot analysis to find the locations that have experienced unusually large numbers of foreclosures. There are several areas of the country that stand out as having experienced especially high levels, seen here in red. So far, we've been able to answer the question, where did foreclosures occur last year? The next logical question, though, is why? What is it about these locations that has led to such high levels of foreclosure? We'll focus on the Denver metropolitan area and take a closer look at the data. Here, the areas in red are the areas that experience the highest levels of foreclosures. We'll be using the new regression tools being introduced in ArcGIS 9.3 to understand why foreclosures happen so we can begin to manage our resources most effectively. Regression analysis is all about understanding and modeling the relationships that exist in our data. In the case of foreclosures, we're looking for the social and economic factors that explain why foreclosures happen. Once we understand why foreclosures happen, we can use that information to model and therefore predict where foreclosures will happen in the future. Creating an effective regression model is all about investigating and exploring our data to understand the relationships that exist. What we're looking at here is a scatter plot matrix, which is one of the new tools being introduced in ArcGIS 9.3. This scatter plot matrix allows us to do some exploratory data analysis and begin to examine the relationships that exist between individual variables in our data. A perceivable diagonal line would represent a strong positive or negative relationship between variables in our data. The bottom row of scatter diagrams in our scatterplot matrix shows the relationships between foreclosures and several individual variables, such as the debt ratio of homeowners or the diversity index of an area. What this scatterplot matrix is showing us is that none of our individual variables are showing a very strong correlation to foreclosures. And what that tells us is that foreclosures is actually a very complex problem that cannot be explained using one single variable. Instead, creating an effective regression model of foreclosures is going to involve several variables. And in order to understand and analyze the relationships between a combination of variables, we'll have to move to a regression analysis. After investigating our data, we're now looking for what combination of variables significantly contributes to the occurrence of foreclosures. We're going to begin with a linear regression tool, which has been added to the Spatial Statistics Toolbox called Ordinary Least Squares, or OLS. OLS allows us to predict one variable, in this case foreclosures, using a combination of related variables, such as the debt ratio of homeowners, the level of college education, or the diversity index of an area. Having run the OLS tool, we can see that the results here are displayed as a map. This map tells me how well the model has performed. The areas in red are where the model has overpredicted the number of foreclosures. The areas in blue are where the model has underpredicted the number of foreclosures. There's also a lot of numeric output associated with the OLS tool. We're interested only in the R-squared for right now. In this case, that R-squared is 0.49, or 49%. What that tells us is that the variables that we chose only explain 49% of the foreclosure story. The reason that our R-squared is so low is that we're dealing with spatial data, and the processes and relationships that we're trying to model often are not consistent across our study area. OLS creates one global equation based on the entire study area to determine the relationships between variables. The problem is those relationships often vary spatially. So for instance, the debt ratio may be a very important piece of the foreclosure story in one part of our study area, but only a very minor factor in another part of our study area. When the over and under predictions of our model are clustered, it means we cannot trust our model. Using a visual analysis of our results from OLS, it is difficult to determine if the clustering of our results is statistically significant. We can use a cluster analysis tool to help us determine if the over and under predictions from our OLS model are in fact clustered. The results of that analysis have told me that the over and under predictions using my OLS tool are clustered, and therefore I know I cannot trust my model using OLS. In order to take into account the spatial variation in my data, I'm going to use a local regression tool, which is another one of the new regression tools being introduced in ArcGIS 9.3. It's called Geographically Weighted Regression, or GWR. GWR, in my opinion, is one of the most exciting and definitely one of the most powerful tools being introduced in ArcGIS 9.3. GWR is very similar to OLS, except that instead of creating a global equation based on the entire study area, it creates focused equations that actually take into account the local character of our data. Having run the GWR tool, the results are again displayed here as a map, which tells us how well the model's performed. The areas in red are where the model has overpredicted foreclosures, and the areas in blue are where the model has underpredicted foreclosures. We can use that same cluster analysis tool to determine if the clustering of our results is statistically significant. If the over and under predictions are clustered, we once again cannot trust our model. The results of that analysis have told me that the over and under predictions from my GWR analysis are actually randomly distributed, which means that I can trust my model using GWR. Going to the numeric output from my GWR tool, we can see that the R squared is now up to 79%, compared to the 49% using the OLS tool. In the social sciences, an R squared of 79% is very high, so I can now feel confident that we found some of the important social and economic factors that explain why foreclosures happen. Once we understand why foreclosures happen, we can use that information to accurately predict where the risk of foreclosures will increase in the future. This map shows the predicted foreclosures for the year 2012. I've applied the model from my GWR analysis to projected 2012 census data. Now that we understand where foreclosures will happen in the future, we can use this information to focus our preventative measures and educational programs on those areas that will need them most. For instance, we can use this information to determine which areas will be most in need of HUD-approved housing counseling agencies. Or, rather than mailing letters to families that are already at extremely high risk of foreclosure, we can focus our efforts on those areas that will be facing foreclosure in the future, and we can address the problem before it's too late. So, using the new regression tools that are being introduced in ArcGIS 9.3, we're able to examine why foreclosures happen, and then use that knowledge to make informed decisions, affect policy, and continue to deal with the significant problem of foreclosures facing America today. Thank you.